Hi, you guys. Clearly stayed home today, but because I didn't want you guys to be all sad that we weren't doing anything with changes in energy, I'm just going to talk you real quick through the notes that we had for today, which, if you remember, on Thursday, the day before burning down the house projects were due, we spent time flipping and multiplying reactions that we knew the change in energy to, and then we'd add them together to find the change in energy for reactions that we don't know the change in energy to. We're going to do this today, but we're going to kick it up a notch because we're Chem X, chemistry to the extreme. Before we make this a little hard, just to review, I'd like you to pause the video at this point and try and use the equations that you're given. Sorry. The equations that you're given here to find the change in energy for the equation that we're given here. So take a minute, give it a shot. Remember, you can flip it or multiply it. And if you flip it, the signs change. And if you multiply it, you multiply the energy by the same amount, by the same factor. Okay, if you've tried it, I'm going to just real quick talk you through how I do this problem. If you read through, or actually look through this problem, starting out with our very first reactant, we have 4 aluminums. I've got a reaction up here that has 2 aluminums, so I'm going to use this reaction. I'm going to keep it the way it is since aluminum is both on the reactant side, but I've got 2 up here. I've got 4 down here. I'm going to multiply this equation that I'm given by 2. And since I'm doing that, I also would have to multiply the energy by 2. So I'm going to write that out. I'm going to have 4 aluminums. Oh, my aluminum got funky there. I'm going to just go with it. I'm going to have 3O2. And I'm going to be making since I multiplied it by 2, 2Al2O3. And delta H for this is going to be that negative 1,676, but times 2. So it's negative 3,352 kilojoules. So now the next reaction, if we look, my next reactant, I guess, in the reaction we're looking for, I have 3MnO2. It's on the reactant side. Here, I have MnO2, but it's on the product side, and I only have 1 mole represented here, so I'm going to have to flip it and multiply it by 3. So I'm going to have 3MnO2. Then I make 3Mn plus 3O2, and delta H, since I flipped it, the sign is going to become positive, and it's going to be 1,563 kilojoules. And so when we add these together, remember the similar things on the reactant side and on the product side will cancel each other out. And in this reaction, I've got 3O2 here, I've got 3O2 here. So if I rewrite everything that's left over, I have 4 aluminum plus 3MnO2 makes, let's do this in the right order, 2 aluminum, Al2O3 plus 3Mn. Delta H then, I'm just going to add these two numbers together. I think I get negative 1,789 kilojoules. So we're going to kick it up a notch. Now we're going to try a problem where I'm not giving you the delta H's for these reactions, but you are going to use your bright green sheet that has the heats of formation. So go ahead and pull that out. We're going to need that, and we'll move on to the next slide. So we are going to predict the delta H, that should be a delta, change in heat for the reaction for the combustion of acetylene, which is C2H2. And we're going to use Hess's law, which is that whole idea that we can add these reactions together. And since I'm not going to give you the reactions, we're going to use those heats of formation, which is the change in energy for the synthesis of everything that's listed on that table. So really all that we're doing is we're going to be writing out our own starting reactions just by looking at that table. I've listed off the steps here. Go ahead and read through those. If we have a reactant, it'll make more sense, I think, on the next slide. Instead of writing the synthesis reaction for that reactant, we go ahead and we show it decomposing into its elements. But still, we're going to keep with a balanced equation. If something has a 2 in front of it, we're going to multiply that heats of formation by 2 as well. If we flip it, we're going to change the sign. So let's go ahead, let's try the next problem. Okay, here's our ChemX extreme styled problem. We're going to find the change in energy for this whole reaction by adding together the heats of formation for essentially all of the components in this reaction. So let's start out with our very first reactant is that acetylene, C2H2, and when you look at the table that represents C2H2, actually on that delta H table, the number that's given for it is 226.73 kilojoules. But since that's the heat of formation table, I'm going to write out, it would be 2C plus H2 makes C2H2. There's the formation for it. That's what that 226.73 represents on that table. But here, you see how this is on the product side? Here we have it on the reactant side. We're going to have to flip it. So I'm going to write that here so it ends up on the reactant side when we add everything together. We have 2C plus H2. And since I flipped it, the energy stays the same, but the sign changes. Oh, what happened? There we go. So negative 226.73, and I think it's kilojoules on the table. If you find O2 on the table, it lists it as 0 change in energy. That's because it exists in its elemental form. That's just how we find it in nature, so it requires essentially no energy to form that. So we don't need to include it. Any elements, they're 0. We don't need to worry about them. So I'm going to go here. The next component in our reaction is our first product, which is the 2 carbon dioxides. So I'm going to write this. We've got CO2, and to make it really good, if we wanted to balance it, I've got a 2 here, so I threw a 2 in front of here. The delta H, the heat of formation for CO2, the gas, is negative 393.509, but because there are 2 moles represented here, I have to multiply that number by 2. So I get negative 787.02 kilojoules. Okay, so now I'm going to do it for our very last product here, and make sure you look at the states. On that heat of formation table, it takes a different amount of energy to form water gas and water liquid, as well as the solid form of water. So make sure we're looking at the correct number for it. I think I did in doing this, but I'm going to write the equation to form water. We're going to take H2 plus 1/2 O2 to make our water, and it matches what's up in our reaction. The delta H for this, since I actually didn't have to change anything about it, is going to be the same as what's on its sheet. Negative 285, I think it's 0.83 kilojoules. So let's add them together. Let's see if we end up with a reaction that's up above. Remember, we're going to cross out the things that are on the reactant side that are the same as what's on the product side here. I can see I've got 2 C's that'll go away. I've got an H2 that's going to go away. And I think that's it for all the things I can cross out. So let's write out everything that's left over. I have C2H2 plus, here I have 2 O2s plus a half, so that's going to add together to be 5/2 O2 to make 2 CO2 and our 1 mole of water. I'm not including the states in there, but they're the same as what's above. And then all I have to do is add together all of those changes in energy, since I've already multiplied everything and flipped the signs. So when we add all of those together, I'm going to stick with our sig figs. We need 2 decimal places when we do that. I get negative 1,299.58 kilojoules is my answer. This is ChemX, you guys. Extreme. Okay, so that last way to do the problem, technically we call that Hess's law. We are adding everything together to come up with the total change in energy for a reaction. It can get messy because you're going to end up with equations everywhere. It's ChemX. That's what we do. But I feel like pretty much as everything goes, there's always an easier way to do things. On your homework, you're going to have problems where it says use the summation method. Way easier. You don't have to worry about flipping anything. You don't have to worry about, I guess, kind of getting lost and canceling things out in the reaction. We simply use this equation. The change in energy of the reaction equals These guys, oh, those are terrible arrows. These guys are the summation, the sum of the change in energy of the products minus the sum in the change in energy of the reactants. This minus is nice because this automatically changes the sign of those reactants for us. So if we were really to plug this in, you take the change in energy of the products and you still multiply those heats of formations by the moles that you have. So I'm going to write this out. I'm going to use, I guess, a bracket. It might be nice here. Our heat of formation for C2H2, it's just exactly what's on the table. Oh, wait, that's not my product. Sorry. You're the products. This guy and this guy. We've got CO2. And on our sheet, its heat of formation is negative 393.509 kilojoules. But I've got 2 moles represented here, so I need to multiply that by 2. And I'm going to add that to my other product, which is water. And I've got 1 mole there. It was liquid water, so it's negative 285.83 kilojoules. There are my products. And from that, I'm going to subtract the heats of formation of my reactants. And the one reactant we're going to worry about is that C2H2. And I'm not going to change the sign. That subtraction is going to do that for us. In my other bracket, when you look at the heat of formation for C2H2 on that table, it is 226.73 kilojoules. And we plug that in. That is way easier than adding together all of those equations. We should get the exact same answer, negative 1,299.58 kilojoules. The summation method, and then Hess's law was simply adding together all of those equations. So tomorrow you guys have the ACT, and Wednesday we are going to come together. We're going to do a lab just kind of proving that we are able to take these parts of these reactants or these reactions and add them together to come up with the change in energy for the whole reaction. We're going to prove Hess's law on Wednesday. But this is it. This is as hard as this gets. I have put online, I'm trying to think, what is it, 16.5. If you had questions on 16.4, we're going to grade that all together on Wednesday, and 16.5 as well. We'll probably have some classwork time if you do have a lot of questions on this. But go ahead and I'd rewatch how I did that last problem with Hess's law. I think that helps. So 16.5, give that a shot, or else keep working on 16.4. I'll see you guys Wednesday. Have fun tomorrow. Bye.